Okay, so let's do this other one that I had started in class. I have the free body diagram. That's this thing over here in blue, so that I don't confuse you. I'm just going to wipe these guys out. So I have the MG and the normal, and in class I was talking about why there was no force from the gray or blue device, this semicircular piece from this guy. There was no force on the point P from that one. So after you sum or you have the free body diagram, you need to sum forces, and I'm going to use r and theta, and so I really need to find the acceleration in using the r and theta. So I remember the formulas. They look like this: r double dot minus r theta dot squared. That'll be in the radial direction, and then I have 2 r dot theta dot plus r theta double dot in the theta direction. Now let's put in the things that I know. I know that r is equal to 2 rc cosine theta. 2 rc. rc is constant. Cosine of theta. So yep, that's what I have there. It says that theta dot is a constant. Theta 0 dot. So this thing is known. Theta 0 dot is known because it's constant. Theta double dot is equal to 0. So maybe I should call this, just so you know, keep it from getting confused, call this W. Right, omega is typically what angular velocity is. It's just a number. I know what that number is, so I don't panic about it. And I know it's a constant. So what I need is, in order to finish the equation, I need the angle, or excuse me, the r dot and the r double dot. So I'm going to do that. So here's r dot. We'll do it by hand. R dot is r and r2 and rc are constants, so this is going to be a minus 2 rc. Derivative cosine is a minus sine. That's why I have the negative there. Times theta. Don't forget the chain rule. Theta dot. Okay. Now, to get the second derivative, don't plug any numbers in until after you finish taking derivatives. I'm going to say that this is two pieces. It is the first term here times the second term. Okay, so I'm going to use a product formula. So that would be minus 2 rc. First term, derivative sign is the cosine of theta. Don't forget the chain rule. Theta dot times the second term. Plus the first term times the derivative of the second term. You can use Mathematica for this as well. Okay, so now we'll plug numbers in, and because now I've got everything I need. So the theta double dot is 0. That's a constant, so this guy is 0. And so my r double dot is equal to a minus 2 rc cosine of theta times, we're going to call that W, right? Times theta dot squared is W squared. Okay, so that's my r double dot. So I'm just going to plug in. So the acceleration is equal to r double dot, that's a minus 2 rc cosine of theta times W squared, minus r is 2 rc cosine of theta times theta dot squared, which is W squared. That'll be in the UR direction, plus 2 r dot is negative 2 RC sine theta. Theta dot is W. So that's 2 r dot theta dot plus r is 2 RC cosine of theta times theta double dot. Oh, well, I should have thought ahead. So that's times 0. That'll be in the u theta direction. Okay. Now that I have these, what I'm going to do is sum forces in the radial direction. In the radial direction, I have, let's label this angle here. Let's see, up here, this guy is going to be the angle theta. So I'm just going to draw a dotted line here. So if that's theta, then this one here is 90 minus theta. So this one here is theta. Okay, so in the radial direction, I have a minus, because the mg, looking at this guy, the mg is inward, pointing this way, and the ur is out that way. So the ur is this in this direction. So that'll be mg times the sine of the angle theta. So the forces in the radial direction is minus mg sine of the angle theta. That's all the forces. That equals the mass times acceleration in the radial direction. So that would be this term right here. This is the acceleration in the radial direction, so it'll be, let's see, we'll put it in black here. That'll be a minus 2 RC cosine of theta omega squared minus 2 RC cosine theta omega squared. We'll sum forces in the theta direction. So I have an NB minus a component of the mg. So it would be NB minus mg. This time it'll be the cosine of the angle theta. That equals mass times acceleration in the theta direction. And the acceleration in the theta direction is this piece right here. So that would be minus 2 times 2 is 4 RC sine of theta times omega squared, or W squared. Okay, so if you count the number of unknowns, I don't know, actually I just, it's the theta that I don't know, and the NB, so the two unknowns. Okay, so I'm going to try and solve this thing. And I think the easiest thing to do is just go to Mathematica and do it. So let me do that. Right, my equations are, let's see, minus mg sine of theta equals, two equal signs, m times parentheses minus, I go ahead and add those together, 4 RC cosine theta times the omega is, well, I'll just call it W. I'll punch it in later. W squared. So that's the acceleration of that in the radial direction, and then second equation is NB minus mg cosine of theta equals And I should put m times g, not mg, so m times g. Cosine of theta equals mass times minus 4 RC sine excuse me, theta times W squared. Okay, I think I've typed them right. And let's execute that. Now what I want to do is solve the equations for excuse me, NB and theta. Alright, and it's very typical to get these conditional expressions when you're using Mathematica. And if you notice, what it is the solution is an angle inverse tangent with a 2 pi times a constant, and that constant is any integer. So it could be 0, it could be 1, it could be 2. So basically, it's the inverse tangent of this angle plus 360 plus 720 plus multiples. So really, you just need the 1. Okay, so let's see. Did they want the oh, they just wanted the angle theta, so I don't really care about the NB. So I'm just going to pull this guy off right here. Let's see. One angle, I have two solutions. One angle is negative inverse tangent. It'll be the negative in the numerator and negative in the denominator. That's going to get me 180 degrees away. That's not the one I want, so I want this one up here that has the inverse tangent of the positive. So I'm just going to copy this guy. Easiest thing to do. It's probably easier just put it in your calculator. And so put it here, and let's put in values of g. G equals 9.81, and then execute this one. Let's see. I'm going to pause. Okay, got a little freaked out on that one when I saw some, but notice the denominators of these guys are all the same. So when I reduce this, it's going to be simply arctangent of 9.81 and 4 RC W squared, because the rest of it is the same thing. So that would be the location where it lifts off. So it looks okay. So if you want to get a number, we'll pick some values for RC. We'll let that be 1, and we'll let the W, which is theta dot sub 0, and we'll let that be 2. And execute that, and then we'll ask for the arctangent. So I'll just copy and paste. Bang. Remember that those are in radians, so if you don't want radians, you just divide by the degree, which is built in, or converted, whatever. It's probably easiest to use your calculator for that. But anyway, so that'll be the 58 degrees is the where it would lift off. Incidentally, I looked back at the problem statement, and it says to find the value that is less than 45 degrees. Obviously this one's greater than 45, but when I checked the solution manual, this is the correct answer. I suppose that if you use different values of R and omega, you'll get different numbers, and it would give you a different angle. So just to demonstrate that, if you doubled the omega, then you'll have 81 degrees. If you lower it, I guess, maybe, let's see what you get now, 22. So depending on what the speed of the theta dot and the RC are, you'll get different values. But anyway, the solution is for the inverse tangent of 4 RC omega squared divided by g, which is what we have here. All right, so now that's it.